Hi everyone, today I present you here my master thesis. It is called Automatic Generation of Verilog Designs for Testing EDA Tools. My name is João Amorim and my advisor is Fernando Pereira. So the agenda for this presentation is to start with the context of this work, then we go through a quick overview of the tool we propose, then the evaluation of this tool, and at the end its conclusion, the conclusion of this work. So to start with the context, we must first understand what is electronic design automation, EDA. EDA is the idea of designing and verifying integrated circuits. So let's think that we have a module that is a sensor controller. It depends on two inputs, the status of the sensor and the status of the switch, and it drives the output, that should be the status of the LED. The body of this module is pretty straightforward. It's just an end between the status of the sensor and the switch, and that's the value that drives the status of the LED. So we want to use EDA tools to first simulate this kind of behavior, then to verify that this behavior is correct, that it does what is expected of it, and at the end to synthesize it. That means to transform it into something that could be written to an FPGA or into an integrated circuit. So the question here is how to test such big and complex tools. The first idea would be to use benchmarks for that, which are pretty useful in many cases, including this one. But benchmarks has a slight problem where they are immutable and finite. Immutable in the sense that unless someone goes there by hand and modify it, it will never change. And finite in the idea of that there are a finite number of designs, and then when we have used every design to test a version of the tool we have, then it makes no sense to run the same benchmark again because we will get the same results. Another tool that could be used instead of benchmarks would be LLMs, but we know that LLMs are pretty expensive to both train and to maintain. So the question in this work is, what else do we got to test on EDA tools? Thinking about that, this work proposes ChiGen. ChiGen is a Verilog fuzzer. It is based on production expansion, and it is not the first fuzzer in the literature. We have, for example, Verismith, Loghammer, and Transfuzz. But different from these three examples, the, the difference of ChiGen is that it is a bottom-up approach, while these three examples are top-down ones. So, what is exactly the difference between top-down and bottom-up? So, top-down is the idea that we start with an empty module and we start to populate it line by line with identifiers and then some assignments and expressions until we have a full module. And for each line that we add inside of this module, we must always assure that the status of the module does not change from valid. The module should always be valid no matter what line you are inserting inside of it. A bottom-up approach is the idea of producing a full skeleton of the module, and then we need to go there line by line, make modifications, for example, type inference and variable renaming to the placeholders that we have. For example, the type something is a placeholder for types, and the uppercase ID, the placeholder for identifiers. After we rename and type check everything, we have a module that's probably valid, but it can sometimes be invalid. So now the overview of ChiGen. The first step is syntax generation, then we have variable renaming, type inference, and at the end code injection. Syntax generation is pretty much based on the idea of the PCFG, which stands for Probabilistic Context-Free Grammar. A PCFG is just like a CFG. The only difference is that the rules, in this case the program producing a module, has some probabilities associated with them. So we see that the program produces a module with 100% of chance, Here the module can produce the literals of the module, the name of the module, a semicolon, and decals, which are a list of declarations, and the semicolon and the literal and module with 81% of chance, while it could produce the same module but without the declarations, an empty module with 19% of chance. The decals non-terminal can produce itself and then a single decal with 92% of chance, or just the single declaration with 80% of chance. The declarations can be both wire or hag identifiers. Okay, so that's the idea for the probabilistic context-free grammar. We just expand the non-terminals until every non-terminal has reached or a symbol identifier or a terminal. So that's how we produce new designs. And the next thing to talk about is about the context depth. To talk about it, we just need to focus on the module and the decals productions. And in this case, we have the context depth of 0. That means that we have no context, only the current production, which should be decal, module, or decals. So this is an example of an AST that could be generated from this CFG. It starts with the module produces a decals, and the decals can produces another decals or only decal, a single decal. So let's see what happens when we increase the context from 0 to 1. In this case, we need to add the context for each production. So we need to know that the module is always produced by a program. So the program enters as the context for the module. So we add program tiled module. The same thing is going to happen to decals. We see that the module comes before it, so we add module tiled decals. But we have another decals, and these decals come from the other decals. So we have decals, tiled decals, and it generates the same thing as module tiled decals. Oh, the difference here is the set of probabilities associated with each rule. It changes based on the context, and that's what modify how ChiGen produces the designs based on the context. So how do we get the PCFGs that we use for this work? We basically have here KaiBench. KaiBench is a Verilog benchmark. With 50,000 designs. We just sorted every design by the number of tokens they have inside of it, and we chose 10,000 designs around the median of these list. With that, we have 10,000 designs. We just get each one of them, build the AST, and just count how many times each rule happens, and that should be the probability associated with this rule. We have used 1 to 6 grams, where 1 grams means no context, only the current production, and 6 grams means 5 grams of context, 5 productions as context, and 1 gram as the current production. Now let's talk about variable renaming, which is the next step. Variable renaming is when we replace placeholders for actual symbols, actual identifiers. So let's see an example. We have here a module. It has 2 inputs and 1 output. In the bottom of it, we have a declaration. Then we have an assignment where the left-hand side has been accessed as an array, and another assignment where in the right-hand side we have the AND operator. So to start, we must first rename the name of the module, which is pretty straightforward. Then we must instantiate the parts, in this case ID0, ID1, and ID2. And the same is going to happen with ID3. You just instantiate these identifiers as valid identifiers for the module to use in its body. And here we need to choose one identifier to actually be used. So we have 2 options here, ID2 and ID3, and that's because we cannot use inputs in the left-hand side of one assignment. So, okay, so in this case we chose ID3. Then the same is going to happen in here. We could be using ID0 or ID1, and we randomly choose ID0. Here again, we choose ID2, then ID0, and at the end ID1. So basically the basic idea of variable renaming is that we go through the entire body and the parts of the module, and we look for available identifiers that we could use, and we choose one of them randomly between the options that we have. Okay, so the next thing about variable renaming is scope creation. Scope creation is like, let's say an example. We have here this module one. It has two inputs, ID0 and ID1. We can refer to both ID0 and ID1 by the name because during renaming, ChiGen is capable of tracking of the identifiers that are defined as parts of module 1. So because of that, it can refer to the name of both ID0 and ID1. The last thing about variable naming is instantiable namespace. Instantiable namespace is like when we have a packed struct. In this case, we have ID0 and ID1 declared inside of ID2. Cadence must also track where ID0 and ID1 are being declared so that we can refer to them by following all the instantiable namespace correctly and causing no errors to the designs. So the next step is type inference. Type inference is when we concretize types. Type concretization is pretty much replacing type placeholders for actual Verilog and system Verilog types. Here we have the same example that we used during variable renaming. In this case, we have these types to replace. To replace type, we must first build constraints. And these constraints are between compatible types. For example, here we have ID0. ID0 is being used in the same context as ID3. So we add the constraint ID0, ID3. ID0 is also being used in the same context as ID1 and ID2. So we simply add these three constants that's saying that everyone there are compatible, ID0 and ID2, ID0 and ID1, and ID1 and ID2. In this assignment, actually in this expression, we have an AND operator. So we add the constraints that both ID0 and ID1 must be scalar values. And here ID3 has been accessed as an array. So we add the constraint that ID3 must be a vector. After that, all these types will be replaced with actual Verilog types. Everything is going to be a wire in this case, except ID3, which is going to be an array of wires. So now the last step of the overview is code injection. Code injection is what grants us control over the design size. And that's basically, let's think that we have this module called module way, and we want to make this design bigger without modifying the internals of module way. So we could simply add other two modules, B and C, to the same file, to the same design, and we would add instantiation between them. So we randomly choose A and B, and we add an instantiation in A of B if A is capable of, it has the number and the types of identifiers in order to fulfill B's signature. The same thing is going to happen with C. The only important thing that we must keep in mind here in this step is that we cannot introduce cyclic instantiations. Cyclic instantiations is when A calls B and B calls A. That would generate an error in this case. So in order to avoid that, we keep two lists, one list of the available modules and the other one of the callable modules. Once A instantiates B, we remove A from the list of callable modules, saying that no other module can call A. In that case, we can avoid cyclic instantiations. And by creating this hierarchical tree, we can add some hierarchical references which can happen in three different ways. The first one is top-down. For example, if A wants to access something inside of C, it can refer to the instantiation of C. So int c.var would read the value of var inside of C. The same thing could happen bottom up when C wants to access something inside of A and it knows that A instantiates C. So we can simply add a.var. And the third way is when B wants to access something inside of C, but there is no direct path between B and C. So in that case, it must start referring from the top module, A, and follow all the instantiations until it finds C. So a.c.var, and that's the basic idea of your coreferences. Now let's talk about function invocation. Functions are naturally generated by the syntax generator in ChiGen. The only thing that okay, so let's see an example. We have here module 1, and we have an input ID1. We have this function, which is called ID9, and when ID1 is 1, ID9 is also 1, else ID9 is 0. The only thing we need to manually add is the call for this function, because we cannot do that automatically with the syntax generator. That would require that we have some context of the program during that step, which we do not have. Uh, why we do that? The reason we do that is because we want to make use of the code that is being defined inside of this function and not just waste this valid and valuable code. So that's the end of the overview. ChiGen is capable of generating 60% to 70% of valid designs, but must keep in mind that invalid designs are still useful. They help us find more edge cases and more tricky cases that perhaps valid designs could not find. The steps of generation, renaming, and type inference are the steps that control the acceptance rate. So if we want to change that, we must modify these steps. While code injection increases the diversity of what is generated by ChiGen and also the coverage in tools. Now about the evaluation, this work has 5 research questions. How diverse are the designs, then how they compare with real-world code. The third one is which kind of bugs can it uncover. The fourth is what is ChiGen's throughput. And the last one is what is the effectiveness of the different techniques applied. Because of time constraints, we're only going to talk about research question 2 and 3. So let's start with research question 2. It is talking about coverage, and we are going to analyze line coverage in variables parser. ChiGen is going to be compared against KaiBench or real-world codes, Verismith, Transfers, and VlogHammer. KaiBench is a benchmark written by real persons, and VlogHammer always produces the same 3000 designs. So here's the plot. In the x-axis, we have the number of designs used. In the y-axis, we have the line coverage in percentage. Here at the bottom, we have in green VlogHammer, in brown Transfers, and in blue Verismith. The solid colored lines are ChiGen grams, and the dotted red line is KaiBench. We can see that most of the grams are really stable, under 15% of coverage, while ChiGen grams reach almost 30%, and KaiBench reaches a little upper 35%. And what is really interesting to notice here is that all the other grams, all the other fuzzers, I'm sorry, they are really stable. I mean, after 1000 program generate, none of them increase the coverage, while KaiGen's behavior is like an increase over the quantity based on the quantity of designs that we use. And that's more like what real code would look like as we see in KaiBench. KaiBench increases in some steps around 1000, 4000, and 50,000 designs, while KaiGen is more like a continuous increasing. So it is not just like what real code would look like, but it's very similar to what it does. The next research question is about bugs. So ChiGen has found 13 bugs in EDA tools, 6 in Verible Suite, 4 in Verilator, 2 in Icarus, and 1 in Yosys. And I'll show you 3 examples of real bugs that we found using ChiGen. The first one is issue 4598 in Yosys. Here we have the local param ID1, where ID1 is equal to itself. And we have another module called module 0. The module is not so interesting for us right now. The problem is really in here. Since ID1 is equal to itself and Yosys understand that this design is a valid one, it tries to optimize this local param. It tries to expand the value of it. When it tries to do that, to optimize the ST that is going to be generated, it starts, it must first expand the value of ID1 in order to expand the value of ID1 itself. So it enters an infinite loop. And this infinite loop will only stop when Yosys runs out of stack space. So it basically kills the process in this case. Here we have issue 1225 in Icarus Verilog. We have a module 0, a gen var ID6, and a for. The problem here is that in the for we have no valid stop condition, and Icarus accepts this design as a valid one. In this case, it freezes computing the range of this for, and it also allocates a lot of heap memory in order to compute for ranges. So here, Icarus will only stop when it has consumed all the available memory in the machine. The last issue that I'll show you is issue 2359 in variables formatter. Here you have a module 0 and one assignment to ID9. The problem is that these two minus operator are seen as one unique token by variables formatter, what breaks the parsing of the rest of the sentence. So this is ChiGen, that's what we proposed in this work. ChiGen is a Verilog fuzzer. It is capable of generating designs with 60% to 70% of acceptance ratio. It has reported and fixed issues. Many of the issues that we have reported to open source tools have already been fixed and shipped with the current version of these tools. And it shows a higher coverage than the other fuzzers that we have tested with. Of course, it has some limitations. For example, we cannot have control over the semantics of the designs that we generate. Something that, for example, an ILM could do, but ChiGen cannot. And currently, we do not support full system Verilog features, but we are working on that. For example, right now we are implementing support for classes from System Verilog in ChiGen, so that's a work in progress. And that's my presentation. Here is my contacts and my advisor's contact. So thank you for the attention.